Hello, this is Brett from SurvivalComms, and today on the bench we have a balun for a Barker and Williamson terminated folded dipole model AC 3.5 to 30. It's not often that you end up getting to cut inside of one and see what makes it tick. So that's what we're going to do today, because you can see it was damaged here, and I'm going to go ahead and see if I can cut along here with a hacksaw and remove this cap and rebuild the antenna. So what is the Barker and Williamson AC 3.5 to 30 antenna? The basic design itself is the granddaddy of broadband continuous coverage HF antennas, and the family it belongs to is known as a terminated folded dipole, or T2FD. It is a non-resonant antenna, typically 4/10 of a wavelength at the lowest frequency of operation and length. It uses a balun transformer and a non-inductive resistor across the folded part of the element. Its popularity in commercial and military circles is as a set-it-and-forget-it HF antenna perfectly suited for ALE operation. And if one is in the market for a modern HF link establishment radio, this is typically a recommended antenna, as it requires no intervention whatsoever across its designed frequency range and is fairly forgiving in installation faux pas. All that glitters is not gold, however, and the antenna has a reputation as a giant dummy load in many circles, but we have to look at it through the lens of frequency agility over terminal performance. Quoting from the 1987 Barker and Williamson catalog, when compared to a resonant dipole on the lower frequency bands, the AC 3.5/30 radiates a signal approximately 2 S units below a dipole cut to a certain frequency. At higher frequencies, there is gain over a dipole because of the length of the AC 3.5 to 30. Refreshing to see a manufacturer that is honest in advertising compared to the dumpster fire of claims from many contemporary manufacturers and vendors. The AC 3.5 to 30 uses a 16:1 transformer coupled with an 800 ohm non-inductive resistor. Many other expressions of this antenna design use a lower value resistor and transformer. I am rebuilding this antenna as true to the original as I can from patent documents available online. The original elements were destroyed by the zero-turn mower, and I was told that the extrication of said elements from the mower was an extremely unpleasant task. Here's our transformer removed from its enclosure. I had to cut both ends of the enclosure to withdraw the device intact, as almost 100% of the device was encapsulated in foam. The construction of this device is very impressive in my opinion, and the interconnection points are wire wrapped and completely flooded with solder. All of the connection points in the transformer, everything is soldered together. The selection of hardware in the construction of this device is of excellent quality. The wire for the transformer at all of its structure points is laced and tied like an aviation wiring harness. And the core material, the wire, the insulation, the whole kit and caboodle appears to be lacquered after construction, so very cool. Here is our transformer sweep under conditions of open, short, and load. The load we selected was 800 ohms. It is a 16:1 transformer, so that's good, and our short and open are both high where they should be. Now let's open up and examine our 800 ohm non-inductive resistor. Now we come to our resistor network, and it's obvious over this antenna's lifetime that we had some moisture trapped within the enclosure causing this rust. The resistor network consists of 6 4-inch by 1/2-inch tubular resistors wired in parallel, which, if my math is correct, would indicate a value of 4,800 ohms each, and each should be capable of dissipating 50 watts to fall within that quarter of transformer RF power window. Resistance across the network is 833 ohms, indicating a 5% component tolerance. Well, we got our resistor network cleaned up. I used ballistol, a bore brush, and some pipe cleaners, and got most of the corrosion out of here that we saw earlier, and a lot of that was flux that was left over from when they assembled all this. I used some Never-Dull on the connections and the wires here, and the good news is, again, is this is going to be completely serviceable for our use. Okay, this is how we're going to rehouse our resistor. The resistor itself is too large to fit into a 2-inch piece of PVC. The original housing for it was this fiberglass tube, and you can see it fits perfectly in that. Now what I've done is I've cut this down. I've taken a couple of these couplings here and I've hogged them out, and I will use the existing PVC to tie these two together, and then I'm going to go ahead and assemble this with AB epoxy, and then I can put these caps on the end of it, and this will press in all the way like that with the PVC cement on either end, and it'll be approximately the same size, and the caps themselves will actually provide support for the resistor inside the housing. Okay, here's our resistor pre-assembly here. We have our two caps, we have a cutout that I make here, and that's to assist with the assembly, and then we can see our housing here that I've completed with a couple of drain holes, and this is our hardware right here, which is just simply our 8 32nd eye bolts, stainless steel construction, and we're going to use nylon lock nuts. This image shows the relationship of the resistor network and the cap. The caps will be close enough to the resistor to inhibit its movement in the housing, yet provide enough space to allow it to cool. And here is our assembled and completed resistor network under test right now. You can see 833 ohms. And you can look at the body of it here, our drain holes, and here are attachment points here. Here's how I went at rehousing the balun. I reused what was left of the original housing and set the length of the unions to allow the balun to reside as shown within the housing. The short cap is just going to cap the top of the balun after providing enough backfill of foam to just allow positive retention of the transformer within this new housing. Now the original RF connector didn't have enough shank to allow it to be used with this cap. So I've configured it as shown, affixing it to the cap with 2 stainless 440 machine screws and nylocks. I also drilled 2 drain holes. The body of the RF connector side of the balun input also has a stainless 440 star lock in conjunction with the nylock. And on the bench we have our completed balun. We have our element attachment points, cap on the top, RF connector down here. I've painted it forest green. The wire I've chosen for the elements of this antenna is 14 gauge bare flex weave. I've got a 300-foot roll of it here from Ham Radio Outlet. Typically I buy wire and cable in bulk because I do this stuff every day, and you can see that I like flex weave wire much better than copper weld. It's much easier to roll up and to deploy than copper weld wire. Now I'm going to start to build the 4 horizontal elements. So I cut 4 46-foot lengths of the flex weave wire. Here are the partially completed horizontal element sub-assemblies. I terminated the horizontal elements for the balun and the resistor. I prefer to not permanently mount the elements to the balun so I can service the antenna, reduce or increase its footprint as needed. And to do this, I use these little donuts that I tie between the eyelet of the balun or resistor and the element loop here. And then I just use a simple fisherman knot here to secure this. Now this gives us a durable yet sacrificial field serviceable attachment mechanism. The element loop is made with crimp ferrules, and the tail of which forms a drip and service loop in the electrical termination of the element. The electrical connection is made with a number 8 ring terminal that is crimped and soldered and covered in glue-aligned heat shrink. Now what I've also done to these ring terminals is I've opened them up to a certain degree, and what this does is this allows me to snap this over top of the number 8 eyelet and remove it as needed. And this electrical terminal is sandwiched between 2 stainless flat washers, and it's secured to the equipment with a stainless nylock nut. Okay, we've got our resistor network and our balun attached to this piece of 1¼ PVC, and we've used stainless steel hose clamps to make that happen. You can see the details of that here and up here. It's very strong. I prefer to have a rigid support in these type of antennas because it's been my experience that both of these devices are considerable in weight and require you to put an awful lot of tension on the antenna in order to keep these spaced evenly. So this right here eliminates that necessity because it gives us a nice perfect spacing of 18 inches at the feed point. And over here's our RF connector. Now you'll also see down here that I've removed the paint and I've constructed this right here. Now, one of the tools I have in my toolbox is a blue sky mast, and this right here is the perfect bore diameter for the blue sky mast sections, and this gives it enough space away from the aluminum mast to reduce its potential for interfering with the operation of the antenna. And the detent pin comes out, and this is just to give you some idea what I'm talking about. You can see our resistor network, balun in the support, and you can see the way this PVC goes together here with our detent pin and how it sits in the bore of the blue sky mast section. Now, would I leave this arrangement set up during a hurricane or something of that nature? No, I would not. However, for a field deployment, something like this is ideal for this particular antenna system. Now we assemble our spreaders. I used 1/2 inch portable water PVC pipe for the spreaders and cut 6 of them to a length of 20 inches each. I made through and through 1/4 inch penetrations, 1 inch inboard from the cut ends, giving us an element spacing of 18 inches. I then painted them forest green and capped them with vinyl caps. Now we assemble our end support arms. I used 1¼ inch Schedule 40 PVC pipe for the end support arms and cut 2 of them to a length of 22 inches each. I made through and through 1/4 inch penetrations, 1 inch inboard from the cut ends for a support cordage spacing of 20 inches. Then made an additional pair of 1/4 inch through and through penetrations, 2 inches inboard of the cut ends for the 18 inch element spacing. I painted them forest green and capped them with vinyl caps. I took the wire element sub-assemblies assembled earlier and attached them to the transformer and resistor support assembly using Fisherman knot loops of 550 cord as discussed earlier. Pay out your element wire evenly for the length of both elements. I then took 3 spreaders and thread them on the wire elements as shown. Now this is how I bring my elements and fold them together. Go ahead and take one of your spreaders and move it out towards the end of the antenna, and remember you've cut both of your wires to an even length, so you're good there. Now go ahead and fold over and bring each element to the very edge of the spreader, and then I use wire ties to secure the spreaders. And it works good on this wire. There's a little bit of movement where you can move them around and adjust. Now go ahead and place your crimps on and make your loops. Giving yourself about an inch. Now you can see what we've done here. We have both of our loops. Now what you'll do is you'll go ahead and apply a crimp to these 2 crimp ferrules, and then take your elements, cross them over like this, and wire wrap 3 times in either direction, opposite twist. Now flood your splice with solder, and this is what you should be presented with. Well, now that we've completed our antenna elements, let's talk about how I attach the end support arms to our antenna assembly or element assembly. I merely took and made 550 cord fisherman knot donuts. You can see it moves around quite well, and these are easy to change if you had to do so with any kind of cordage you happen to come across. And you can also separate this antenna element assembly and perhaps replace it with a shorter one or a longer one, whatever have you, and still use these end supports. So the whole system is modular in that regard. Now for our end tie-off point, I've chosen to use mule tape, and you can see that I've just used the same 550 cord fisherman knot donuts here and tied bowlines around here, and then I tied a loop at the end for our end tie-off point. And you'll notice that it's offset in relation to the end support arm. This is the top and this is the bottom. What's important to remember is that if you tie this off in the center or you tie off this offset on this end of it, it tends to allow the antenna to rotate, and that's not desirable. So offsetting this as such prevents that from happening. Well, here's our antenna in its transport configuration, and it's painfully obvious that this antenna occupies a lot of real estate even when stored like this. Now when you do deploy this antenna and you stow it, it's important to make all of your wire wraps as even as possible to keep everything even. And it's also a good idea to have a couple of these like cardboard shipping tubes right here to wrap the antenna around, and then I've just tied it again with little mule tape wraps there to keep it in one piece, and then I can take the whole doggone thing and roll it up like that and stow it in a bag with the blue sky mast. So now we're ready to set this antenna up and test it, and our control antenna for the testing is this, which is my field deployable ZS6 BKW, and it's easy to see just how much less real estate this antenna occupies than this particular antenna, and they're both around 90 foot long, so there's really no advantage to using this antenna over this one besides the broad frequency coverage, and we're going to see how they stack up against one another. The transceiver I used in this testing is my home-built microbit, and no antenna tuner whatsoever was used in any of this testing. Here is our initial sweep, and it is pretty much what we expected. 60 meters is a bit disappointing, and perhaps altering the length of the antenna a few feet would help, as 90 feet is pretty close to a half wavelength of 88 feet for 5.3 megahertz. Now in a non-resonant design such as this, it's no bueno. Note that the dips in the sweep favor non-amateur spectrum, which, considering the marketed to end user of this antenna, makes sense and further supports the idea that altering the length of the antenna may be a worthwhile experiment at some point, but the performance increases realized would not be profound in my opinion. On a side note, the auto tuner in my Pro 3 made short work of matching the antenna on 160 meters, but the observed terminal performance was awful. Now let's start our whisper testing. The first up is our control antenna, the ZS6 BKW, mounted at 20 foot on a fiberglass mast supported by the blue sky tripod. This is 40 meters, and local time was 2 in the afternoon, which is not the ideal time to use 40, yet here we are. There was a good balance between stations received and stations that received my signal. Now we have moved to 20 meters for this testing sequence of our control antenna, and our results were much better overall. And again, we saw an excellent balance between stations receiving my signal and I receiving theirs. Now we have reconfigured our antenna system and have the T2FD mounted at 20 feet on the blue sky mast on 40 meters. Local time here was 3 in the afternoon. The radiation pattern seems to differ from our control antenna a bit, as you can see. Another observation was that the ratio of stations hearing my station as opposed to me hearing theirs diminished in comparison to the control antenna. This is likely due to the resistor network eating up RF in lieu of radiating it. Now we have moved to testing our T2FD on 20 meters, and you can see that our antenna gave a good account of itself in this sequence. However, the test antenna did fall short of our control antenna in observed performance in the ratio between received signals and others receiving our signals. What we have here are two antennas receiving the same station using the same SDR using an antenna switch to switch between the two antennas. The use of an SDR isn't used here to give us an absolute value, but rather a relative value for comparison purposes. We are targeting a station on the 40-meter band, and we can see our control antenna is receiving our target station signal at a level of minus 78 decibel milliwatts, and it appears that our noise floor is at minus 115 decibel milliwatts. Our S meter is at S8. Our test antenna is receiving the same signal at a level of minus 84 decibel milliwatts, with our noise floor appearing to be in the neighborhood of minus 105 decibel milliwatts, or an S7 on our meter. What we can see from this particular data is that the ZS6 BKW is outperforming the T2FD on this particular signal, and that it is meeting or exceeding the window of expected low frequency performance outlined in the original marketing materials. Now we have moved to targeting a station on the 20-meter band to capture some data. On our control antenna, we can see the station's signal is minus 90 decibel milliwatts, with our noise floor appearing to be minus 115 decibel milliwatts, or an S6. On our test antenna, our signal is minus 94.3 decibel milliwatts, and we saw a small decrease in our noise floor by perhaps 2 dB, giving us an S5 on the target signal. Again, our control antenna outperformed the test antenna in this instance. Now let's sum up my opinion of this antenna. I will do so in a pros and cons format, concluding with the best practices recommendation. The pros of this antenna are first and foremost that the antenna is capable of operating across the HF spectrum without a tuner. It is delivered assembled and has a set it and forget it functionality. This particular antenna is capable of handling a kilowatt of CW or data in intermittent commercial and amateur service. Durable construction. This antenna is several decades old and was used at legal limit over its lifetime before I salvaged it, and subsequently it was run over with a zero-turn mower, twisting the elements into a Gordian knot of wire. The only failure of the core components was in the compromise of the ballon housing. The high-tier models of this antenna use stainless elements and have a price point to match. Finally, it's a time-tested design. This means much more than many realize. These antennas predate the internet and internet marketing and are still used extensively in professional circles for a reason. They work. Now let's move on to the cons. The first one is that the antenna, at the end of the day, is a compromised antenna, and it should be looked upon as such. One way to look at it is as a dummy load with elements between the load and the transformer. The best way to equate the performance I observed is that it exhibits similar performance characteristics on HF that you would see of a VHF discone at VHF and UHF. The antenna is not particularly easy to deploy in the field. The elements should be deployed and stowed carefully, paying attention to winding it on a tube greater in diameter than the end supports, adding to the parts count. I made mention of the weight of the core components mid-video,
And in order to support the antenna from the ends only, you need really stout objects as anchor points, and fiberglass poles are a total no-go. The amount of end tension required to do this necessitated the use of ratchet straps. Now, center supporting the antenna and a rigid mast helped considerably, holding or enabling the tension of trucker hitches and bank line to be sufficient to hold the antenna taut. Large form factor, stowed and deployed, this antenna takes up a lot of real estate. Although the antenna overall lengthwise is shorter than, say, an 80-meter doublet, it is really hard to tell. When aloft, the antenna really stands out, so if stealth is a consideration, another design would be worth looking at. And finally, we come to expense. This antenna with stainless elements is $1,800, and the less expensive ICOM or other commercial variants are in the $400 price range. You could certainly build your own and save a few $100 if you chose to do so. Now we're going to close with my opinion on the best practices for use of this antenna design. This antenna is best used as a fixed location HF antenna for an end user that requires full HF spectrum coverage that is limited to one antenna. The antenna installed as a flat top in the clear between two telephone poles with a self-tensioning mechanism at greater than 30 foot above ground level. And if desired to use in the field, field use requires motorized transport and a rigid center and well-tensioned end support. I hope this helps. This is Brett from SurvivalComms. Till next time.